All right, we are going to continue our examination of Maxwell's equations in the context of prerequisites to QED. So it's a very formal examination of Maxwell's equations. As I've been saying over and over again, we're going to do it in reciprocal space eventually, but we've been sort of stuck in real space because it's a really rich topic, and I want to squeeze all the prerequisite juice out of it that we can. And now that we've gotten the potential formulation down, that is, we've written the Maxwell's equations as two second-order differential equations, that counts as a different form of Maxwell's equations. The question kind of is, though, how different is it really? Because if you look at regular old Maxwell's equations, and when I say regular, what I mean is we're treating electric field and the magnetic field as vector fields, regular vector fields, and we've got four first-order differential equations, first order in time, first order in space, because these are differential operators. And yes, we have compressed it into two equations. There's no doubt about that. But they're two second-order differential equations. So the actual mathematical content and complexity and sophistication is arguably not improved, right? So today we're actually going to see about actually improving the knowledge density of these equations. And we are going to take Maxwell's equations and write these four equations in tensor form, right? Tensor form. And the goal here is to understand this notion, this principle. I can take the electric field and the magnetic field, and I can transform them from one reference frame to another reference frame, from one Lorentz frame to another. I can make these transformations. And if I do that, and I substitute the transformed fields into these four expressions, I'm going to get the exact same four expressions in terms of these transformed fields. The problem is that's certainly not obvious. We would have to execute this transformation and then plow through the mathematics and simplify things to get all of this written in prime, 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 prime. Like, we'd have to do that. And it would take a long time. But the fact that it is true is a big hint that we can create a relativistic form of this that uses what we call manifest Lorentz invariance, which means that these equations will be not only, they are Lorentz invariants, but we're going to be able to write them down in a form that demonstrates the Lorentz invariance just by their visual structure. Ultimately, there is an improvement, a mathematical density improvement, so to speak. And the idea is, with mathematical improvement should come some sort of interpretational improvement. So that's what we're going to do today, and let's begin. So we have already worked pretty hard to understand the vector potential, which is these three components of the vector potential, ax, ay, and z, which we write as A. Now that we've mastered this vector potential idea, and we also learned about the scalar potential, now that we have these two potentials, and we understand the relationship to B and E, our first step into unifying Maxwell's equations into a tensor expression is to first unify these two potentials together into a four vector. And that four vector we call the four potential, and its first component in SI units is the scalar potential over C, and then AX, AY, and AZ, the three components of the vector potential. Now this is in one frame of reference. So we're in some reference frame, some inertial reference frame, and in that inertial reference frame we have a vector potential that's a function of x, y, z, and t, and we have a scalar potential likewise. It's a function of x, y, z, and t. And we're going to combine these two together into a four potential. Now first, to be clear, that's not an arbitrary step. You can't just take any four things and make a four vector out of it, or line them up and call it a four vector. We have to be confident that this object actually, we have to understand what it means to be a four vector. And the idea, of course, is that if I switch to a different reference frame, a different Lorentz reference frame, that's going to be a Lorentz transformation of exactly the form that we learned about in earlier sections of this lecture, right? So we now know that we can take this Lorentz transformation matrix, take our 4 potential, and transform it to a new Lorentz frame using the architecture of this Lorentz transformation matrix. That's what it means to be a 4 potential. So now you could ask the question, well, how do we know that this is a 4 potential? That we can make this construction, that we know that this is the case? So that's a good question. And the answer is actually kind of tricky, but we're not going to go into it. That's one of the rabbit holes we are not going to go down. You can Google it. It's not, the proof is actually a little bit more subtle than you would imagine, or the understanding is a little more subtle than you would imagine. But for the purposes of getting into QED, this is a 4 potential, and this transformation is true. We're going to do this again for the 4 current, right? We're going to write the 4 current down as the 3-dimensional current density J, which we've already discussed, which is a function again of x and t, and the charge density, which is a function of x and t. And we're going to combine those into a 4 current as well. And when we do that, what we mean is that we can transform it using a Lorentz transformation matrix. And this is the matrix that we spent so much time getting familiar with earlier, and now we're getting the payoff. Okay, so with that first step, we now need to understand that the way we're going to construct this is with 4 potential components, right? So this is the contravariant components of the vector 4 potential. These are the covariant components of the vector 4 potential. And these minus signs are introduced because we are assuming a mostly minus metric for our work. Right? We're going to use SI units. The SI units is really ultimately what this C, where this speed of light constant comes from. And we are going to use this mostly minus metric, which is constant. So we're flat space-time and the mostly minus metric, which means whatever, even if you're in spherical or cylindrical coordinates, you could always transform to Cartesian coordinates, and every point in space-time would have this value for the metric. And when you lower this index using this metric, you're going to introduce these minus signs. So that's using this very classic standard formula depicted right here. So that's the first step, is we have to now, in order to simplify Maxwell's equations, we have to realize that our vector and our scalar thing is actually a unified object called the 4 potential. And that little unification is what opens the door to creating the electromagnetic field tensor, which is our next subject. Oh, before we move on, I actually wrote this out a little bit more thoroughly so you could see it. But this notion of transforming using the Lorentz transformation matrix, I'll remind you, we went through in earlier lessons, derived the most general form of this Lorentz transformation matrix. And that general form, I suppose I should take these b's in the denominator and give them parentheses, because they're meant to be the magnitude of beta, the velocity beta, whereas this b here is the second component of beta, right? So beta is a vector bx, or I guess the way I'm writing it, b1 in the x hat direction plus b2 in the y hat direction plus beta 3 in the z hat direction, right? And so it's a little bit sloppy the way I did it, but now I've cleaned it up with these parentheses. But the point is, this is kind of a mess of a matrix, right? You've got this gamma term, of course, and then you've got the components of the velocity, and you clearly are going to mix up all these components of the 4 vector potential together, the 4 potential together, to get the 4 potential in the new reference frame. And what's interesting about this is, and if we just did a boost in the x direction, for example, this is how it would ultimately look if you calculated the new components. But note, by the way, there's a little bit of a subtle trick here. Remember that that AX is a function of X, Y, Z, and T, right? And when I do this transformation, when I multiply these matrix elements by this column vector, I end up with AX, AY, and AZ on the right-hand side. But what's interesting about it is this expression here, right? Let me change color. For example, this expression right here, right? That expression is A prime X, right? A prime X, or I guess you could say it's A1 prime, right? In using our component notation, using this component notation here, that would be A1 prime, right? But using sort of more colloquial notation, you would say it's the prime, it's the prime reference frame X component, right? It's meant to mean the same thing, but let's stick with this guy. But this is still going to be a function of X, Y, and Z, and T. But notice these guys are in the unprimed frame, right? Unprimed frame. So this is an annoying little problem, right? Because you're transforming the potential from the unprimed to the primed system, but you're left with these functions that are still in terms of the unprimed system. So you have to transform all of the x, y's, and z's inside these functions to x primes, y primes, and z primes. So when you study this, don't forget that. And the idea is, why would you want to study it? Well, you might want to show, for example, you might want to prove to yourself that the Coulomb gauge, if this is the Coulomb gauge in the XYZ frame, if you transform to the prime frame, this is not necessarily equal to 0. In fact, it probably won't be, right? But in order to do this check, you have to take derivatives with the prime variables, and you have to make sure you convert this x, y, and z to x prime, y prime, and z prime, not just a to a prime, right? Anyway, so that's an interesting little trick. But that is the point of the value of being a 4-vector, right? Okay, so now with this 4-vector potential, we are going to now derive an electromagnetic field tensor. So we land in Wikipedia, and Wikipedia gives us this beautiful definition of the electromagnetic field tensor, F mu nu, and it does it component by component. As long as you understand that A now is the 4 potential, and these indices run from 0 to 3, right? 0 to 3. And when you do this, and you execute this for each of the possible combinations, for example, F01 all the way to F, 2, 3, right? You will generate a tensor that has components, and each of the components can be expressed as the components of the electric or magnetic field. And with the caveat that you have a few minus signs in there and a couple factors of C. And first thing you can notice from this definition is that F mu nu is antisymmetric, right? If you switch mu and nu, you switch the sign of this thing. And indeed, this whole thing is obviously antisymmetric. The diagonals is 0. That's important. And this is the definition of the magnetic field tensor. F mu nu is the electromagnetic field tensor. And the metric that we're using here for this is the mostly minus metric, right? The mostly minus metric. If you use the mostly positive metric, you just the only thing that happens is, well, all the signs switch. But we're not going to do that. We're not doing that. This is the mostly plus metric. We're using the mostly minus metric. So that's the definition of this guy. Now you know right away that this is a tensor and it's Lorentz invariant, because if you look at this, you see this is a fully indexed object. So clearly, every one of those things is subject to a Lorentz transformation. And you'll just change the mu to mu prime, the nu to nu primes, and you'll have an expression that's true in the new frame. So F mu prime nu prime will be true. So this is a field, an electromagnetic field tensor. Now, what you don't have to worry about so much in this prerequisite work is my whole mess, I call it a mess, I shouldn't call it a mess, I'm very proud of it, but this whole notion of a tensor should never be separated from its sort of unit vector part. It's the part that makes it a tensor. This, in other words, is simply a component, a real number, right? This guy here is the actual tensor piece that, grabs, that's either, that grabs, that makes it a vector space, right? And if in the what is a tensor series, I spend a lot of time on that. But you remember, even in the what is a tensor series, I eventually say, now that you understand this, we can actually see why we can give this up and do everything in terms of the components. And I'm not a fan of that, right? I mean, anybody who did that course knows I rail against it. On the other hand, you can't follow me around everywhere and, do what I say. You've got your own books to read, and you've got, and clearly Wikipedia has no trouble with it, as we see right here, right? Wikipedia does not have, partial mu tensor product, partial nu stuck next to that. So clearly, you can't live and die by that ideal, that pedagogical ideology is, I guess, what I'm saying. So anyway, there's the tensor. And clearly you see already that we have now unified these fields into a single mathematical object. And they really do lose their identity because once we have it in tensor form, we think of it as universal to any possible Lorentz transformation that's out there that's interesting. And once you start Lorentz transforming this guy, the E fields and the B fields completely get mixed up, and they lose their independent nature. So once you start thinking of the electromagnetic field tensor as something that has validity in any Lorentz frame, clearly you realize that the E and B fields do not have meaningful invariant natures. And this actually becomes the fundamental physical object. And now, arguably, you could say, well, are we elevating the physical nature of the four potential, right? If this stuff is completely scrub now, well, this is a tensor, but so is this expression. Maybe these vector potentials are more important part of nature than we thought. And yeah, that this would definitely imply that, right? This would definitely lead one to start thinking, well, maybe the four potentials are fundamental, the fields are not. Now, you still have the problem of ambiguity, though, right? You have this ambiguity of the four potentials, and that just doesn't go away. It just doesn't go away. So, there's a lot of debate to be had here, but it's interesting to track the debate because you start understanding the nuts and bolts of what you're doing. Okay, so now let's see, how does this four potential actually give us these fields? Well, the only way to exemplify this is just to do it, right? The magnetic field is the curl of the vector potential. Now, this is the vector 3 potential, right? So this is our elementary form where we have a vector and a curl of a vector is a vector, so this is all good. And when you do this calculation, when you do this curl, you get the derivative of the third component, the derivative of the second component combined together with this sum together with this minus sign there, relative minus sign between them, and that's the x component of the magnetic field. It's this spatial derivative of these two different components of the vector potential. Likewise, the y component of the magnetic field is a similarly structured object. So now, if we look at F mu nu and we look at its definition, we realize that, okay, there's only so many components that aren't zero, right? We've got the diagonal is zero, so let's forget those. Those are clearly going to be zero. But F12 is the partial derivative of the second component of the 4 vector. Now, this is a 4 vector, so this would be the y component of the magnetic potential, vector potential, and it's the first spatial derivative of that minus the second spatial derivative of the first component, right? I'm trying to find words to describe these derivatives. But regardless, clearly partial 1 component 2 minus partial 2 component 1 is this guy here, and that's the z component of the magnetic field. That is Bz. And sure enough, that's what I've got here. That is Bz. And if you raise these two indices using the metric, you learn that Bz is not only the F12 component of the fully covariant form of the magnetic field tensor, electromagnetic field tensor, it's also the fully contravariant form, right? In other words, raising these two indices it doesn't change a sign. Sometimes you get a sign change. Actually, for the electric fields, you do get a sign change, as you'll see in a moment. So you can calculate this for all three of these, and you do end up with this minus By. And remember, it's antisymmetric, so F13 is equal to minus F31, which is equal to minus F21 up here, and this one will be equal to minus F32. So all of you have a lot of these little weird index things going on, but the point is that the spatial part of the tensor, meaning the part that has no index that's 0, are all related to the magnetic field, right? Except for the diagonal ones, which are 0 because of the antisymmetry of our definition. Now you can do the electric parts are a little bit more interesting because you still just run the same definition straight up, right? F01, you just put in the 0 for mu and 1 for nu and write it all out, and that's what you get here. And then you get partial A1 with respect to x0, and then you get this A0 now is the scalar potential over the speed of light. So you end up with this 1 over c out here, and you get the scalar potential with its spatial derivative with respect to x1. But remember, x0 equals c times time. So if I convert that to a time derivative, I get a 1 over c out here, and I end up with ex over c as the answer for the 0, 1 covariant component of the magnetic field tensor. So that's where these little c's come from when you do it. These x0s, when you have it with respect to time, end up having pulling out this 1 over c, right? So, and the reason we did that, by the way, is so we could use our definition of the electric field, which is dA dt, not dA dx0. If it was dA dx0, you would have to include another factor of c in this definition, for example, but we don't. So here you can see if I pull the c over here, I get the definition of the x component of E from our vector equation that connects the electric field to the scalar potential and the vector potential. So that's good. And we do that for all three of them, and we get Ex, Ey, and Ez. And now we do introduce a minus sign. And just to see how that works, remember, F mu nu, to raise, so if I have lowered indices alpha beta, to raise it, I use this formula right here. So if I want the raised 1, 2 formula, I execute this sum, and what makes the sum simple is that all the off-diagonal terms of the etas are 0, right? So I lose, I don't have many terms in the sum. I only have one term that survives. But G22 and G11, they're both minus 1 in a mostly minus convention. These two guys are -1 and -1, so they cancel. So now, for the spatial parts, for any two spatial parts, any totally spatial piece of the electromagnetic field tensor, the two will cancel, and the covariant and the contravariant components are going to be the same. But when you have only one spatial part and you have a time piece, G00 is 1 and G11 is minus 1, so you don't get a cancellation of minus signs, so you introduce a minus sign here. And that explains why these minus signs appear on the right-hand side. Okay, so the point is now I've shown you the compact construction of the electromagnetic field tensor and how using these potentials in their four-potential form, using the four potential, which takes our magnetic vector potential and our scalar potential and combines it into a four-vector, we use that to define the electromagnetic field tensor, and you can see how the components of the electromagnetic field tensor, as defined this way, gives you the fields embedded in this object. And now the fields are in the rear view mirror, and it's just this tensor that matters in our physics. So hopefully we're going to be able to write all of our physics in terms of this tensor. Well, that would be the goal. All of our laws of physics could be written in the terms of the tensor. Okay, so what do we do next? Well, one thing we should do is, since we discussed the idea that the Coulomb gauge is not going to survive a Lorentz transformation, right? The Coulomb gauge will not survive a Lorentz transformation, but if we look at the Lorentz gauge, right? The Lorentz gauge is it's not, this zero is a bit of a mess there. This is the Lorentz gauge, and explicitly executing the sum, you get this string of this expression of four of these partial derivatives with each component of the four potential. This sum basically has to be zero. I'm just blowing up the Einstein notation there. But the point is now you have contracted indices up and down. You don't even have to go through this process of checking this arbitrary matrix against an arbitrary field and calculating the transform field and then showing that this transform field still has this property, right? In other words, you don't have to check that partial mu a mu equals 0, a mu prime, right? Switching into the new reference frame. You don't have to check it because the Lorentz condition is all obviously relativistically invariant, because if we assume that A is a four vector, this expression is completely contracted space-time indices, which by definition, that's how they're constructed. That's what it means to be completely contracted. It means everything. This is a Lorentz invariant expression by its very nature. And that's why we say it's manifestly Lorentz invariant. If you have these indices structured in a reasonable way, that's all you need to know. If you can put your expressions in that form, you have created manifest Lorentz invariance. And, if you really wanted to go in there, I could take a mu and transform it with a Lorentz transformation, and I could take this mu, this partial mu, that's a space-time index. I can transform that with a Lorentz transformation. And this becomes a prime, and this becomes a mu prime, and this becomes partial mu prime, and a mu prime, partial mu prime equals 0. That's the Lorentz condition in the new frame of reference. And I always can't resist, but this is a constant in flat spacetime, so you can pull them out, and you get these two Lorentz transformations that contract to 1, which again shows you that all these Lorentz transformations done right really are multiplying by the identity matrix in the end. Okay, so that's one thing, is that's why the Lorentz condition, the Lorentz condition is valued, right? Is because you can make all these boosts and nothing happens to it. Now you'll see when we quantize things that there is some flaws with this. You introduce degrees of freedom that you have to get under control, but so does the Coulomb gauge in a way. The Coulomb gauge has its own issues, right? So the point is I just wanted to demonstrate what they mean by manifestly invariant. Okay, so now we tackle Maxwell's equations. We've got a new form for the fields. It's all buried in electromagnetic field tensor. We have a four potential. Now we need to make Maxwell's equations work. And so why not go to Wikipedia to talk about this? Here we have the two inhomogeneous Maxwell's equations, right? We have the charge density and the current density, and everything here is a regular vector. This is a vector, this is a vector, B is a vector, rho is a scalar, but the divergence of a vector field is a scalar. So that's all a scalar equation. So if we want to now turn this into something that just uses the electromagnetic field tensor, we actually have to, it turns out, create yet another 4-vector called the 4-current. And this is the construction of the 4-current, just as stipulated right here in Wikipedia. The time component of the 4-current is the speed of light times the charge density. And the space component is the current density. And combined together, that gives you a 4-current. And that 4-current, what that means is you can transform this from one Lorentz frame to another using our lambda matrices all day long. But once you've done that, now the claim is that this is the two inhomogeneous Maxwell's equations combined together into one very tidy statement. And notice that this tidy statement, they're still first order. This is still a first order differential equation, but instead of two, you have one. And the sheer notation density is much improved. So this, in sort of the way the parlance of the business is, if you can express complicated things in a simple way, you're learning something, right? You've improved your physics. You've improved your interpretation of how nature is organized mathematically. So the idea is to say that this is the favored mathematical way of writing it down because it takes something that was complicated and makes it simple. Now, there's a lot to say about that because obviously we know that buried in here is actually a big mess. So you can almost argue, well, no, I'm just hiding stuff under the rug, right? I'm hiding things, and this is not actually any simpler. It's just I've defined things in ways that make it look simpler. That's probably not true. It's probably actually is a better way of looking at nature. It definitely captures. It's manifestly Lorentz invariant, first of all, right? Because alpha is contracted, and you're just left with naked space-time 4 vectors on both sides, so it's very clean. Lorentz invariance is a fundamental part of physics, but these are Lorentz invariant too, right? You're not going to. It's just not obvious that it's that way. Now, so you can argue about this, but the point is that this is a very, very important form to understand. You can't go marching into QED without having a good grip on this form. But notice we did have to create another 4-vector here, but that just tells us that the current is actually a 4-vector, which is important too. So then we do have two other Maxwell's equations, the homogeneous ones, right? The homogeneous because you've got zeros on the right-hand side. And those get squeezed into this new form related to what's famously called the Bianchi identity. And this can actually be compressed even further because you note that the permutations of the indices are all, it's completely, it's appropriately symmetrized, right? You just shift the alpha, beta, and gamma comes over, right? You're going to go, alpha will go here, beta will go there. Let's see. Beta will go there, and then gamma will go there, right? And that's alpha, beta, gamma. And then likewise, alpha will go there, gamma will go there, beta will go there. And that's what this is supposed to say. Now, the only reason you can get from here, just to be very clear, the only reason you can get from here to here is because F beta alpha equals minus F alpha beta, right? The point being is that this really is 6 terms, and here's 3. But you can combine these 6 terms together because using the anti-symmetry of F, right? So that's very important to understand. But the point is that, again, you've simplified everything down quite a bit. And in fact, this is the way to look at it, right? We had 4 Maxwell's equations. These two get compressed into 1, and these two get compressed into 1. I guess for the time being, I'll let me move this away so it doesn't sort of spoil the look here of getting compressed into 1. But this isn't a legitimate compression, because you've now got first order differential equations, but only 2 of them. Your mathematical objects are more general and have wider applicability, and they are easier to interpret, right? This can be interpreted in terms of ideas of differential geometry. This is a 4 divergence, right? So now instead of having a divergence and a curl, you have 1 4 divergence. And this divergence and curl turns into this Bianchi identity, which is really convenient. So this is really nice. Let me quickly I think I need to do the demonstration that this and this are the same. So let's check that out. So we begin by understanding, what are we after here? We're after, in one particular Maxwell equation, the divergence of E is equal to the charge density over epsilon naught. And this divergence is defined through this combination of spatial derivatives of the various components of E. It's a scalar, divergence of a vector field is a scalar. So somehow this has got to be buried inside our new definition of Maxwell's equations, right? I shouldn't say our new definition, our new form of expressing Maxwell's equations, which we're going to work on this 4 divergence of the electromagnetic field tensor equals mu naught times the 4 current, right? So somewhere buried in here has got to be this expression, and likewise all of the other expressions. We're going to demonstrate this for 2 of the expressions. So let's blow up this sum using the standard Einstein convention, and we remember that this is a sum over in Minkowski spacetime. So we have a mostly minus convention, so we end up with these 3 minus signs, but the leading term is a plus, and that is just executing the sum over mu, right, which is a dummy index, right? So we can execute that straight up. And now we see we have 4 equations, one for every value of nu, right? Every value of nu. So because we're dealing with this charge density, let's speculate that the relevant equation takes out nu j superscript 0, because we know that the current density's 0th component, its time component, is the charge density times the speed of light. So let's substitute everywhere we see nu, we'll substitute the index 0. And when we do that, we get mu naught J0, which is now mu naught C rho. Ignore the fact that this is red, and that there's your charge density. But mu naught C, we know that epsilon naught is some combination of mu naught and C. We remember that from electrodynamics, right? So hopefully that'll flush out. There definitely needs to be a C squared in there, so we got to keep an eye out for that. But it's trending in the right direction. And then we get this time derivative, or x naught derivative of f00, but we know that f00 is 0 because we know that f is antisymmetric and its diagonal elements are 0. So we know that this is not a thing. So we now have the x1 derivative of f10, the x2 derivative of f20 minus the x3 derivative of x30. So what we realize right away is that, well, wait a minute, we know that f10 is the opposite of Ex over C, right? We figured that out a moment ago. Let me review that. You may remember back here, we calculated F10 was this partial derivative of the 4 potential, and it ended up being Ex over C. But we also understand that when we raise the 0 and the 1, because the 0 goes up with no sign change and the 1 goes up with a sign change, right? Actually, I think I even did it explicitly down here, right? F01 is going to be the opposite of F01 covariant. F01 contravariant is the opposite of F01 covariant. So F01 contravariant is minus Ex over C. So this becomes minus Ex over C, minus Ey over C, and minus Ez over C, just substituting for the F, right? So when we do that, you can almost immediately see these minus signs become plus signs, right? This becomes Ex, this becomes Ey, this becomes Ez, right? And we have a 1 over C with each of these, right? We have this 1 over C, which we just move to this side, and we get our C squared, and voila, mu naught C squared does in fact equal 1 over epsilon naught. So this becomes epsilon naught. That goes away. This is gone. And what do we have left? We have exactly this divergence equation. So the 0th component of this form of Maxwell's equation, and when I say 0, it looks like, well, wait, you need to specify 2. But no, this is a dummy index here, right? So this is completely contracted away. So this is 4 equations because, and you can tell from the right-hand side, right? It's clearly there's going to be 4 equations here. And the 0th component equation here, or the 0th index equation, returns to us the first Maxwell equation. All right? So now we just have to hunt down the other Maxwell equation that's tied to this expression. And the next one, well, if setting index 0 is so helpful, why don't we just set index equal to 1 and see what happens, right? So now we take this new index and we set it equal to 1. And we examine what we've got here, right? We know that this term is going to go away because it's the diagonal term in the electromagnetic field tensor, which is antisymmetric. And now we have the time derivative of F01 over here. It's actually the x0 derivative of x01. This is the x2 derivative of F21 and the x3 derivative of x31. So what are these values? We just have to substitute what we know these components are in terms of the fields. And what do we discover? We discover that this F01 becomes minus 1 over C E1. So it's the time derivative, or the x0 derivative of E1 multiplied by the constant 1 over C. And what do we get next? We get the x2 spatial derivative of the third component of the magnetic field and the x3 spatial derivative of the second component of the magnetic field. Now, these two are clearly looking like the piece of a curl, right? Remember, the components of a curl are formulated like this. This would actually be the component of this would be the x component, or the x1 component of the curl of the magnetic field. And so it looks like we are now finding the x1, or the x1 component of the curl equation for the magnetic field. Specifically, if we are claiming that these two equations are bound up in here, this equation is a vector equation, right? You have a vector on the left, you have a vector on the right, and this is a vector term. The time derivative of a vector is still a vector. This expression has an x component, a y component, and a z component, meaning this vector on the left and this vector on the right, it's 3 component equations. So it looks like we're hunting down one of those components. And specifically, if we go back up to this example of what a curl looks like, here we see the curl of A, and we see the component of the curl of A is the derivative in the x2 direction of the third component of A minus the derivative in the x3 direction of the second component of A. And that pattern is exactly the pattern we have in our expression right here, right? So this is going to be, if you rearrange it so this term goes here and this term goes here, and you relabel 2 and 3 to z and y, this is the x component of the curl of B. And then this derivative of x1, of E1, this is the derivative with respect to x0, but x0 equals c times time. So if I want to put literally the time in there, I have to pull out a factor of c, right? So there's my c squared, and this whole thing looks like minus 1 over c squared, partial ex dt, curl of B x component, right? And this expression is the x component of the relevant Maxwell's equations. And does it equal the right thing? It equals mu naught J1, right? So I guess I should say this is equal to mu, let's see, mu naught Jx, right? And there you have it. So we do this 3 times, meaning we go back here and we replace nu with 2 and 3, and we'll get all 3 of the relevant components, right? We'll get a y and a y, then we'll get a z and a z, and now we have 4 component Maxwell equations. These 3 here we could combine into one vector equation, reproducing it as we're used to seeing it. And there you have it. So you can do the same thing for the other two Maxwell's equations, right? You can do the same thing for these two, the homogeneous equations, and plug, just expand this out, right? And once you expand it out, you'll discover embedded in it are these two Maxwell equations. So big success, right? We have now shown that we can take these 4 Maxwell's equations and these 4 Maxwell's equations here, we can compress them into these 2 equations. And notice these are tensor equations. They're not vector equations, they're tensor equations. So you're solving for the components of the electromagnetic field tensor, presumably given a charge and current density that you can combine into a 4 current. You're solving for these components. And you use a lot of the fact that this is asymmetrical keeps the number correct on both sides. The number of equations and the number of unknowns is still all good. So with that, now the question is, okay, so this is what you need to know as a prerequisite. You definitely need to understand Maxwell's equations in terms of the electromagnetic field tensor. This is something that I just can't imagine arriving at any reasonable form of QED book anywhere and not having a very good understanding. The problem is QED books sort of know when you get there that you may not know this very well. And they do a little bit of review, and it's good enough, but the point, if you're here, you're worried about superficial knowledge or knowledge that requires a lot of evolution before you really feel comfortable with the subject. So hopefully what we've done is we've given you the motivation to dig a little bit deeper and gather up and exercise this. Matt, for example, you can do this yourself. You can find these 2 equations by doing this. Just take note when you do solve this yourself, meaning when you go through the exercise we just did, mu and nu can't take the same value, right? So that eliminates a lot of options. So, you pick mu nu and that you don't have to go through every conceivable combination of these indices, right? In fact, a lot of them are absorbed for you because this is all the cyclic combinations present right in front of your face. So there are just as many expressions here, in other words, as there were here. So now the question remains is, have we gone as far as we can go? We've definitely gone far enough. Let me make that clear. We have gone far enough. You can stop right here if you're interested in just the prerequisites for QED, but I simply can't resist pointing out one other thing. And in particular, you can ask the question, well, I've taken 4 first-order equations and turned it into 2, and if I count the number of pen strokes it takes to write this stuff down, I suspect I've improved the pen strokes. I can improve pen strokes here too, right? I can write this as, I think, partial alpha f mu nu, and then if I put brackets like this, I think that's we're compressing this notation using these brackets that symmetrize things. So, I've definitely reduced pen strokes. I've increased information density at the expense of having to know the definition of this, right? So I'm always kind of curious, are we making progress in the sense that we are truly unifying things? And, the idea now is that, F is now the basic thing of our study, but we've reduced it from 4 to 2. I guess the obvious question that floats around my head, at least, is can we go from 2 to 1, right? Is it possible that we can actually create just one equation? Now, to be honest, the answer, as far as I understand, is yes, it is possible. The question is it worth the time it would take to develop what is required to do it? And I'm going to strike a compromise with the caveat that we are done as far as the prerequisite promises. This is the prerequisite material. I cannot help but simplify this yet again. One more layer of simplification I think it's worth doing. And it fits very beautifully in with the what is a tensor material that we did before. So I simply can't resist it. Unfortunately, the simplification I offer doesn't really get us to the 1 point. What it does is it takes this equation and this equation and writes them even simpler than they are, but you still are left with 2 equations as far as I know. Taking the step all the way down to 1 equation, at that point I'm not really an expert, but there is a field of study that I am interested in learning that does do it, and so I may do a video on that as I learn it. That's a subject called geometric algebra. But using the language of differential forms and the machinery of the exterior algebra, we can write down these 2 equations in a much more, I want to say intuitive, but in a much more logical format than just this purely tensor format. Well, I guess I can't say it's more logical. I mean, there's nothing illogical. If there's 0 illogic here and there's 0 illogic in something else, it's not like one's more logical than the other. But the exterior algebra form is very beautiful and it's very telling. And honestly, I guess if you really understand the exterior algebra, it's quite intuitive. But so we'll do that. I'll do that as a supplementary lecture next time. But the truth is, and the irony is that no matter how far you push this, when you solve E&M problems, you always kind of go back here, right? I've never seen anybody solve a waveguide using the differential forms analysis. And now that I've said that, I'm sure 1 million people are going to point me to references where it's done, and I'm going to be impressed. But the point being is that just because you can go from this 19th century version of things to this 21st, let's see, what century are we in? We're in the year 2000, I guess that's the 21st century thing over here. Doesn't mean that this is useless or this is old, it's definitely old, but it's not obsolete in any way, right? Okay, so So what have we done today? We have shown that Maxwell's equations can be expressed in this purely beautiful relativistic form. We discussed a little bit about the relativistic invariance of the Lorentz condition, not Lorentz condition, the Lorentz condition. I've learned that recently. And we demonstrated how these vector expressions, these classic vector expressions, are buried inside these tensor component expressions. And next time what we're going to do is we're going to take a bit of a divergence into a bit, we're not going to take a divergence. We're going to divert ourselves a little bit away from the mainstream notion of prerequisites of QED, and we're going to show how exterior algebra can arguably simplify these two equations even more. Okay, I'll see you next time.